Hi, Sim. Okay, come, let's start. We shall not wait for the answers. We shall continue with the redox reactions or redox process. I written this last week. What are some of the possible redox reactions? So obviously there are more than that. Hold on, Sim, let me undo, unshare, and share again. All right, let me know if you can see the screen now, Sim. Okay, now, yeah, we have written this last week. These are some of the possible redox reactions, but obviously in real life, there are more than this. Now that I'll just quickly go through the examples. I realized I didn't do that last week. Angel, Xin, can you see the screen now?
Yes.
Okay, good. Some Angel, give me an example of combustion. Combustion. What can be combusted? Or what is combustion? Okay, not sure. I'll just give you one example. Let's say you have coal or even charcoal. And you will be asking what is the chemical formula for coal charcoal. Essentially, it's made of mainly carbon, so I can write it as C. Okay. Oh, by the way, this is just one example. There are obviously many, many examples of combustion. What else do you need for combustion, Sarah? What's the other reactant you need for combustion, for something to burn? Heat. Okay, besides that, what's the other reactant? Okay, this one must know, everyone. You need oxygen. Combustion is actually burning. And you need oxygen for all combustions. In this case, your product is only CO2. But for other cases, there may be other products, but we'll just stick to this example for now. Now, the tricky part is this. There's only one product. There are two reactants, so I can safely say that this reactant can be paired to the only product, and the other reactant paired to the only product. The question is, which pair constitutes oxidation and which pair constitutes reduction? Come in here. C to CO2 is. Why? Yes. Guys, try to recall, we did this last week. It gains oxygen, so therefore I classified this as oxidation. And automatically, you should know the other pair must be reduction. O2 to CO2. But it's not so obvious. Is O2 gaining oxygen? Is it losing oxygen? No, you can't really tell. Is it gaining electrons? You can't really tell either. Right. All right. So for O2 to CO2, we'll leave this for the last definition, which is regarding oxidation state. By singing, you just sit there. Okay, I'll give you the worksheet or the notes. Okay, so for O2 to CO2, I'll leave the definition as to the explanation as to why it's reduction for later. Look at displacement next. Well, I did mention. Okay, I did mention displacement is always a redox reaction. Bouncing in. Any example of displacement? Oh, okay. I think you skip a few lessons already. Yeah, my angel, back to you. Displacement? Oh, no. Okay, I'll just go through an example I did some weeks back, I think. So displacement can involve halogens. So if I have Cl2 and Ki, okay, this was covered in the other chapter. Sarah, have you come across displacement? Displacement, yes. So what will I get here? I will get KCl and I2. So this is what we call displacement reaction. Oh, just to give you some background, essentially Cl2 displaces iodide and Ki to I2. Okay, that's how you write the displacement description. Oh, but of course they may ask you to explain because Cl is more reactive than iodine. And in this case, I'm concerned about specifically about group 7 or group 17. Okay, so that's an example of a displacement reaction. But, oh, recall, how do we define redox? There are 4 ways, remember? Michelle, give me one way to define a redox reaction. By looking at, you had this table or something like this last week. You either look at oxygen or hydrogen or electron or oxidation state. OS stands for oxidation state. Okay, so there are 4 ways to identify redox. But look at this guy. Look at this reaction here. Any oxygen inside? No? No? Any hydrogen? Yeah, none. Can you see the electrons? You can if you are good enough. Okay, tell you what. Come, all of you, convert this to an ionic equation. Xingling, you do that as well. If you need help, let me know. Injured? Cancel out the spectator ions. Balance it also. I didn't balance the equation. I didn't balance the equation. Make sure you can balance it yourself. Michelle, done? Sarah? No? Now, guys, just a quick recall. Make sure you balance the equation first. I didn't balance it in case you didn't notice. Then what next? This is, okay, I didn't give you the state symbols either. So this is a gas. This is aqueous. Aqueous. This one is a bit tricky. Let's just put it as solid. Okay, so convert all the aqueous species to ions. So I'm going to write something like this next. Gas remains as gas, no change. But this is an ionic compound, convert it to ions. KCl is also ionic compound, it's dissolved, some more dissolved in water, convert to ions too. This is a covalent covalent element and it's solid, so it remains as it is. Next, cancel out the spectator ions. Ions, I use the word ions, don't cancel out other things, just ions. So K plus, 2K plus, cancel out with 2K plus. Make sure you don't go and cancel 2I minus if I2. Don't do that because this one cannot be cancelled out. I'm only cancelling the ions. So what remains? This is the final equation. Angel, do you get this? The rest, okay, Sarah? Okay, now, but I still haven't answered my question. Based on this, who is oxidized and who is reduced? First thing, try to pair them up. I think in this case, it's quite obvious. Chlorine will pair with chloride. Iodide will pair with iodine. But who is oxidized? Which pair is oxidized and which pair is reduced? Can you look at oxygen? No. Can you look at hydrogen? No, because there's no oxygen, no hydrogen inside. Therefore, you look at electrons. Can Cl2 to chloride, singing, gain or lose electrons? Cl2 becoming chloride. Gain. Okay, so this gain, to be more specific, 2 electrons. Not surprisingly, for the other pair, I minus lose 2 electrons. Check your definition. Who is reduction and who is oxidation? This is what? Lose 2 electrons. Yeah. Okay. Losing electrons means oxidation. And gaining electrons means reduction. Okay, so in this case, you can look at electrons, but the moral of the story, if you want to look at electrons, it's easier to look at the ionic equation. Just keep that in mind. Oh, let's go a bit further. Who is the oxidizing agent? Sarah? This is oxidized. Yeah, so therefore, this must be the oxidizing agent. Okay, because Cl2 oxidizes the other guy. So for your answer, you can write something like this. Cl2 oxidizes 2I minus 2I2. Okay, so that's why Cl2 is the oxidizing agent. It oxidizes someone else. And of course, by right, you should now know who is the reducing agent. It must be the other reactant. If this guy is oxidizing agent, this guy must be reducing agent. So same thing, I write a similar statement. Okay, I minus reduces Cl2 to 2-chloride. Quick reminder, both oxidizing and reducing agent must be reactants. It must be on the reactant side. Don't look at the product side. Singing, okay?
Yes.
All right, sure. Okay, Xingling, your turn. Tell me, what is the Haber process reaction? What's the
Something about
reaction?
ammonia.
You need to know the exact reaction, do you?
I forgot.
Oh. Okay, I assume you have already copied down whatever you need. Xingling, if not, let me know. Okay, come, Haber process. Don't forget, you're supposed to know the exact reaction. Xingling, what's the Haber process reaction? Oh, forgot to. I have nitrogen. I have hydrogen. Quick reminder, it's a reversible reaction. So you use this double arrow. Get ammonia, balance it, of course. And quick reminder, all of them are in gaseous states in the actual process. Same thing. Which part is oxidation and which part is reduction? Now, there's only one product, so it's quite straightforward. Obviously, one reactant goes to the product, the other reactant goes to the same product. But which one is oxidation? And which one is reduction? Come, Angel. This one, what is this? How do you know? Yes, good. This is quite obvious. N2 gains hydrogen to become ammonia. So, look at your definition, which I wrote down last week. Singing, you were not around, but I wrote this down last week. So, gaining hydrogen is classified as reduction. Okay. So yeah, this is reduction. And that automatically tells you the other pair must be oxidation. But why? Did it gain hydrogen? Not really. Did it lose hydrogen? Not really. Did it gain electron or lose electrons? Can't really tell also. So for this explanation, I'll leave it last to the last definition of redox. Okay, so at this point, you can't really tell for sure. This is oxidation, but by default, it should be reduction is already here. This must be oxidation. But the explanation, let's leave it to later. Come, quick one. Sarah, who is the oxidizing agent here? N2 or H2? Okay, this is oxidized. So the other guy must be the one doing the oxidation. And in contrast, this other reactant must be the reducing agent. Okay, so one is oxidizing, the other is reducing. Provided you have two reactants, each you have more than two, then that becomes a bit more troublesome. Okay, so that was Haber process. I will not touch on photosynthesis and respiration. They are not likely to come up for chemistry. I will not touch on these three because they are covered in another chapter, which we haven't gone through yet. So far, questions, anyone? No? Michelle? No? Xing, okay with this table? Okay. Now, let's go to the last part. By looking at oxidation state, oxidation number, you have 7 rules. A, B, C, D, E, F, G, 7 rules. You're supposed to remember the 7 rules, but after you practice enough, you should remember them automatically. Okay, look at rule number 1. Element oxidation number is 0. Okay, tell you what. I'll look at the example then. Let's go back to our example. Let's look at this again. The displacement reaction that we wrote earlier, and try to apply oxidation states. Okay, so how many elements do you have? So what I do is, for me, I write out the equation. Then I normally put OS below the equation, oxidation state. If you want to put ON, oxidation number is fine. The two are exactly the same, either OS or ON. So I need one number for this guy, one number for this guy. Every single element, I need one number. So I need 3 numbers on the left, 3 numbers on the right. Look at rule A. It says that oxidation number of atom in an element is 0. Do we have any element here? In here, do we? Any element? Okay. Cl2 chlorine is an element. So I can immediately write 0. It's an element. This is compound. This is compound. This is, Michelle, element of compound. Yes. So I immediately write 0. Look at rule B, boy. Oxidation number of a simple ion is equivalent to its charge. Any ion? No obvious ion here. They are all in compound form. Let's look at C. Hydrogen, blah, 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 has a OS of +1, but any hydrogen? Nope. Look at D. Oxygen, blah, 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 has an oxidation number of -2. No oxygen either. But look at E. Is there any group 1 elements? Any group 1 elements in your reaction here? Michelle, any group 1 element? Oh, okay.
Okay.
Which one? Yes, potassium is group 1 element and it's in compound form. It's not in a pure element form. So I can write +1 and +1. Reminder to everyone, make sure you have the plus there. You cannot simply write 1. Make sure the plus is there. Next, look at this table. Any group 2 element? No. Group 3 element? No. Any group 17? This 17 actually, because now they change it to 17 already. This is 3, this is 2, this is 1. Any group 17 elements? Singing? Yes. Okay, but we are concerned about group 17 element in the compound form. So iodide is group 17, chloride is group 17. They are in compound form. Okay, these two are elemental form, Cl2 and I2. So this already assigns 0. So what should I assign? -1. Okay. So iodide is -1, chloride is -1. So I have all my oxidation states. Same thing, I try to pair them up. Who pairs with who? Well, the simple answer is iodide pairs with iodine. And the same element pairs with itself. Right? Chlorine pairs with chloride. Now, look at chlorine. It has 0. It becomes -1. I hope you see 0 becomes -1. So what has happened to the OS? 0 to -1 means it has decreased. Therefore, by definition, this is a reduction. OS decreases is a reduction. Look at iodine or iodide. From -1, it becomes 0. So the OS has increased. Therefore, this is defined as oxidation. How come I didn't look at potassium? K. Notice potassium is -1. +1. Potassium on the right is also +1. No change. So I don't bother about potassium. Okay. Next question. Xing, who is the oxidizing agent? Oh, chlorine. Okay. Actually, it's the same answer as before. Chlorine is oxidizing agent. Ki is the reducing agent. Can. Sarah? Okay. Okay. Let's go on to address the earlier reaction, this one. Okay, go back to this combustion, which we did earlier. Now, let's work out the oxidation state also. So I need one number here, one for O, one for C, one for O. Look at rule A. Do I have any elements? Yeah, I do. Carbon is an element, so I immediately put 0. Oxygen, O2 is an element too. 0. But this is not an element. CO2 is a compound. So I look at which rule? I have oxygen, right? I look at rule C, I think. Oh no, D for dot. Oxygen atoms, this rule, assign an oxidation number of -2 except in peroxide. CO2 is not peroxide, so therefore O will be assigned -2. And according to rule D for dot, so O2 is assigned, or O here is assigned -2. Take note, I don't care about the coefficient. Can carbon C in CO2. Which rule do I use? Can I use rule A? No, not really. It's not an element. Rule B? No, it's not an ion. Rule C? No. This only applies to hydrogen. Rule D? Oxygen? No. How about rule E? Can I use rule E for carbon? Is carbon in group 1, 2, 3, or 17? No. All right. Carbon is in group 14, in case you've forgotten your periodic table. Therefore, I have to use rule number F. Read oxidation numbers of the atoms present in the formula of a compound add up to 0. What does that mean? So take note, I'm using rule F. So let's go back here. So CO2 is a compound. Therefore, I can write something like this. I use my algebra. C plus, now I am now concerned about the coefficient. So I put a 2 here, okay, because the 2 comes from here. There are oxygen, 2 of them. And it equals 0. Because this is a compound and it's neutral. So I put 0 here. But what else do I know? I know oxygen has -2, so I sub it in. Therefore, now I solve for carbon. And you should get +4. And I now know that carbon has an OS of +4. Okay, can. Hey, Angel and Sarah, just bear with me for a while. I know you're rather familiar with this. Singing, okay? Michelle. Right, let's go to the last one. How about this guy? Just now we did this reaction too, the Haber process. Work out the OS for all of them. So same thing, make sure the equation is balanced first. Then for me, I normally indicate OS beneath it. I need one number for this, this, and that. Okay, altogether 4 numbers. Is that right there? All right, look at rule A. Do I have any elements? Yes, I do. N2 is an element, so 0. H2 is an element, 0. Look at rule C. C for cat. It pertains to hydrogen, so hydrogen is here in a compound. And by default, it has OS of +1. Can, so H is based on rule C. But how about N? Is there any rule regarding N? Not exactly. So you have to use rule F. Set out your algebra again. So I can write N plus, oh, just be a bit careful, especially for Xingling or even Xingling and Richelle. I do not regard this coefficient. I do not account for this, but I account for 3 here. So I have to put N plus 3H equals to 0. Okay, but I disregard this one in front. So I don't know what's N, but I know what's H. H is +1 based on rule C. So if I solve for that, I will get N equals to -3, which is what I have here. Okay, same thing, pair them up, nitrogen to nitrogen. OS changes from 0 to -3. So it's a reduction in OS. Therefore, yeah, this is a reduction. 0 to -3. Again, I disregard all the coefficients. I don't care about the numbers, or I don't care about the number here. That's the tricky part. You need to know when to care and when not to care. This one, how about hydrogen? H to H. 0, 0 here. H +1 there. So OS has increased. Therefore, this is oxidation. And Xingling. Xingling, I haven't asked you. Are you all right?
Yes.
Okay. Now, one important thing. Let's go back to my table again. This one. O and H may not be reliable because they are not in direction. They may not be in direction. This one, electrons, sometimes you don't see it so easily unless you convert to ionic equation. But this one, take note, this is the most reliable method to define oxidation and reduction. It works all the time, for all reactions. Just keep that in mind. Anytime you're not sure, use your OS to find out whether it's oxidation or reduction. But let's give you one unusual example. Very unusual. Let's say I have this. Only one reactant and only one product. Oh, by the way, O3 is called ozone. Maybe you have heard about it. Oxidation or reduction? This reaction. Quite unusual. Oxidation or reduction? Not sure, right? It seems to gain oxygen. Seems to. How about let's try working on the oxidation state? So I should have one number here for O, another number here for the other O. Only two numbers. Come, Angel. OS. OS. Good. Guys, both are in elemental form. So OS will be 0. Both O2 and O3 are elements. There's no change in oxidation state. So therefore, this is not a redox. Can keep that in mind. Sometimes your question may give you non-redox reactions. You find that all the OS have no change at all. Okay, questions, anyone? No? Now, since you are all impure, the bad news is the exceptions will be coming up. Where are all the exceptions? Or the unusual examples here? Except, look at rule C, in ionic hydrides, where the OS is -1. This may come up. The second exception, except peroxides, where the OS is -1. OS of oxygen. And there's one more exception. I repeat, for pure chem, they like to ask about exceptions. This is the last one, except for fluorine. When it's combined with O or F. So 3 exceptions to look out for. One of them, at least one will come up. Serious, please highlight them. At least one will come up, maybe 2. Let's look at the first one. What's a hydride? I'll give you a few examples. So let's say I have this. Looks funny, but it's a salt. Okay, this is a hydride, and they call it lithium hydride. Not surprising. Maybe this. Now, of course, this is called magnesium hydride. Okay, the thing is this. You still have to work out the OS. So I need one number here, one there, and one there. Singing OS for lithium. Good. Group 1 element is in a compound, so it's +1. And since I told you it's a hydride. H is -1. Okay, it's not +1 anymore, it's -1. Oh, by the way, just to elaborate, I hope you realize, as I said, it's a salt. So it contains of two ions, lithium plus and H minus. Okay, these are the two ions. H can be -2. Keep that in mind. So if I look at them as ions, then it becomes pretty obvious, right? +1, give you +1 OS, -1, the charge -1 gives you -1 OS. Now, of course, I can do the same for magnesium. Magnesium, Michelle, OS. Yes, good. It's in group 2. Now, since this is hydride -1, please don't go and account for the 2 here. Don't bother. Don't go and times 2. Please do not times 2. It's still -1. Okay, can. How about this? Peroxide. What is peroxide? I'll give you the most common example, which is likely to come up for your exam, even for practical. H2O2. Oh, yes. So, student size to control. This will be used to cover the last 4 lessons.
Okay, this one, the country cooking has 5 lines. Yeah, this one.
You will let us know the number you can ask us.
Oh, yeah, I want to check, I check. Yeah, usually what is the time from one?
You mean operating hours? It's not fixed because the thing is, there's no admin staff station here. So it's only open when the lesson going on. So the best is if you're coming down, let us know before.
I want to like the latest.
Oh,
The
latest.
latest treatment.
That's to 90.
Okay, so then by 7 start.
Yeah, 7:30 to 9.
Maybe it's the school lunch. First,
Yeah, of course.
you want the one to what? Yeah,
Yeah.
if you.
Let's go back here. Hydrogen peroxide. Remember this guy, please. It comes up often, very often, even for practical. How does it look like? It's colorless. It looks just like water. It's a colorless liquid. Not surprisingly, it's soluble in water. So it can be in solution form. Okay, so this is called hydrogen peroxide. But there may be you may see others too, like this. Looks funny, this one. Looks funny, right? You think that is a typographical error. It's not. This is magnesium peroxide. It's not often encountered. So if you see something funny, suspect that it's a peroxide. So of course, if I write my OS, this is magnesium is still +2. Oxygen is no longer -2. It's now -1 because it's a peroxide. Okay, anytime you know it's a peroxide, OS is -1 for oxygen. Look out for that. But back to our friend, H2O2. I don't know. It may just come up for you next year. This one, even in practical. Let's say I give you this reaction. Oops, sorry, H2O. I just give you this reaction. I want you to balance the equation, work out which is the oxidation and which is the reduction. Balance it first and work out which pair is oxidation, which pair is reduction. Do you want to use OS Do you want to look at hydrogen or do you want to look at oxygen? Whatever the case, balance the equation first. Oh, enjoy that. Okay. Mm, okay, I mean, I can still accept it. Okay, I can still accept it. Richard, no? Sarah, no? Let's start with OS. Maybe you want to work with OS first. And I need to have how many numbers? 5 numbers, huh? Okay, now it's an odd number, which is possible. 5 numbers rather than 6 or 4. I need 2 on the left, 3 on the right. Singing OS. Good. This one. Good. Good. Guys, you should be able to find all this OS based on the rules. Remember, this is peroxide H2O2, so O will be -1. But water is not peroxide, so the O is -2. Just be very mindful about this. So then I try to match that. Of course, look at H +1 on the left, +1 on the right, no change. So I don't look at H at all. H is not, there's no change to this OS, +1, +1. But look at O. From -1, it becomes -2. OS decreases. Therefore, reduction. I look at O again on the left and look at O2 on the right. From -1, it becomes 0. So OS has increased. Therefore, this is oxidation. Okay, so be careful. You can have 1 reactant as well. So who is the oxidizing agent then? Guys, in this case, there's only 1 reactant. So it is both the oxidizing and the reducing agent. It's possible. So keep that in mind. Can, Angel? Okay. Maybe I write something for you in case this comes up. So how would I describe this kind of reaction? I would write something like this. So H2O2 is reduced to H2O, and I mean, if you want to be grammatically correct at the same time, oxidize to O2. Okay, can in terms of the description. Oh, but let's say somehow you have a problem with OS, you're not that competent with OS. Can I look at it another way? Well, it's possible. Let's say I have the same reaction again. Okay, okay, I don't need to, I'm not going to balance it, but look at this. What's happening? H2O2 to become O2. What is happening here? Rather than looking at the OS, can you tell that it's losing hydrogen? Okay, and by definition, losing hydrogen means oxidation. Okay, likewise, what happened here? H2O2 to H2O. What has happened? It has lost oxygen. And by definition, losing oxygen means it's a reduction. So this is an easier way, but I can bet that your exam question will ask you to use OS. They'll force you to use OS. You have to write out all the OS. It will happen, 100%. It will. Okay, so that's that. Let's look at the last exception. Oh, any questions, anyone? Xingling, are you fine?
Yes.
Oh, okay, good to know that you're still there. Now look at the last one. This one. Chlorine. Be careful when you see chlorine with, let's say, oxygen. Now let's give you an example. Let's say you see this guy here. What is this? Well, no need to know the name, but I want you to work out the OS. There are three elements. It's a compound, obviously. Angel, OS for sodium. Yes, it's in group 1. Oxygen. Yes, look at rule, is it C or D? I think D, D for dog. Okay, this is not a peroxide. So oxygen will be -2. Chlorine, this is the difficult one. It's now combined with oxygen. So please do not write -1. It's not -1. Because chlorine is combined with oxygen here. Anytime you see O and Cl together, be very, very careful. This has come out, I think, in this year's O level. Be very careful. What's the OS then for chlorine, Angel? Yes. This is not -1, instead is +1. How do I get it? Well, the safest way is to use your algebra again. So sodium plus oxygen plus chlorine equals to 0. Sub in the values that you know. +1, -2. So if you work it right, chlorine is +1. Okay. Okay. Okay, let's give you one more. If I give you this ion. Oh, we haven't done any ions yet, right? Okay, let's say you have this ion. Come guys, work out the OS. Only 2 numbers because there are only 2 elements. Obviously, chlorine is combined with oxygen, so this is an exception. Xingyin, done? Not sure. Sarah? Oxygen? Chlorine? +2. Angel, what do you get for chlorine? Fraction. Let me see. Did I make a mistake? 1, 2, 3, 4. Okay. 4 now. One, did I make a mistake? No, I didn't. Okay, come. Let's work this out using algebra. 0, oh, not 0, oxygen. Now, when you use your algebra, you have to account for this 4. That's the dangerous part. Sometimes you forget. 4 chlorine equals to what? Now, take note. There's a charge here. So I have to account for that charge as -1. Okay. Oxygen is -2, so I sub it in. -2 plus 4 chlorine equals to -1. Solve for chlorine. What do you get? Hold on. What did I miss out? Oh, okay. Yeah, I made a mistake. I made a mistake in the formula. Okay, my bad. This is the correct formula. Still, you have 2 OS. Come, India, chlorine. Okay, oxygen. Come, guys, you're supposed to get these 2 numbers. Michelle, can, okay. So, moral of the story. Look out for this, guys. Then, when you see chlorine, if it's combined with oxygen, look up because chlorine has 1, 2, 3, 4, 5, 6 possible oxidation states. It depends on what the exact ion that is combined with. Only for chlorine, it has this unusual property. Just be careful if you see chlorine. It comes up quite a bit over the years. No need to know their names, except for the first 2. Okay, the rest, just know that they have different oxidation states. Okay, last one, last part. I like this TMNO form. They like to have this in the exam, even for practical. It's called potassium manganate 7. The other one that they like to come up is potassium iodide Ti. Highlight this as well. These 2 are very popular. Why? Because they can change color. That is the main reason. Now, guys, I want you to remember, hopefully, for now, from now till your O levels, KMNO4 is purple. It is purple. Anytime you see a purple solution for O levels, 100% is KMNO4. Now, the other thing is, maybe you want to add into your notes, it's a strong oxidizing agent. It can oxidize a lot of things, which also means it can easily react with reducing agents. So guess what? That implies it can test for reducing agent. Because it reacts with reducing agent. Okay, and the trick is this. What happens is this, no need to know this equation, but MnO4 minus, once it is reacting with a reducing agent, it becomes Mn2 plus, and there's a change in color. Purple becoming colorless. Okay, so keep this in mind. Anytime you see a change of color from purple to colorless, a redox reaction has occurred. Remember that change, purple to colorless. Now, the other thing I want you to do, hopefully you can tell, KMNO4 is made up of K plus and MnO4 minus ion. Come guys, look out the OS. 1, 2, and 3. KMNO4 is made up of K plus ion and MnO4 minus ion. What are their ONs? Sarah, this one. Okay, good. Mn? Good. O? I want to emphasize on this. Notice that, look at the name, potassium manganate. Oh, by the way, this is 7. This is the Roman numeral for 7. Why 7? Because of this. Manganese is 7. So basically, this Roman numeral refers to the OS. In this case, OS of manganese. All right, so that's why it's 7 here. Okay, anyway, just remember this guy, potassium permanganate. It tests for reducing agent. Now, all of you have done QA, right? Have you? Qualitative analysis, the chapter. Qualitative analysis, test for anions, cations, gases. No, not yet. Oh, okay, that means not yet. Now, remember your QA, which test involves the use of KMNO4? Cl2. Which one? Not Cl2. Anyone can remember? Oh, nobody remembers. Let's show you the QA list again. If you have it, of course, you can refer to it. Yeah, good. Now, Sarah, have you seen this before? No? Okay. We'll go through this one other days. Michelle, you've seen this, right? Now you go to the gases. Look at SO2. It turns aqueous acidified potassium manganate to from purple to colorless. So this one you're supposed to remember. What does that tell you? It tells you that SO2 is a reducing agent. Okay, keep that in mind. Because it can react with KMNO4, which is an oxidizing agent. Okay, that's all I want to say for this. Or for the sake of Sarah, so basically potassium permanganate can test for SO2. Okay, because SO2 is a reducing agent. Now, let's look at the second one, potassium iodide. This one comes up all the time. Make sure you're familiar with this, potassium iodide. Why? Because it tests for oxidizing agent. Let me wait for this to be restored. Okay, so take note, this can come up in your practical as well. So Ki test for oxidizing agent. Okay, can. But let's go back to our example. Go back to your displacement reaction. This one. Okay, you did it just now. Displacement reaction. Okay, I hope you have written everything down. Okay, so because I'm going to erase some of it. Yeah, assume you have worked out all the OS already. So now let's look at another layer. Appearance. Okay, Cl2. Oh, let me give you the state symbols too. This one, I'll write it down later. Right. Now, Angel, Cl2, how does it look like? Oh, what's the appearance of Cl2? It's you can describe it as greenish yellow or yellowish green. Yes, obviously. Ki appearance. K is a group 1 element, it's not a transition element. So you would expect it to be colorless as a solution. KCl? Well, same thing. It's in group 1, it's not a transition element, so it's a colorless solution too. This is the tricky one. Now, just now I told you it's a solid. Yes, it is, but this one you may want to take notes. It can partially dissolve in water. So I can actually write aqueous here as well instead of solid. Oh, this one you have to remember. I2 dissolved in water. What is the appearance? This one you must remember, highlight it. It's going to be a brown solution. You do not see many brown solutions around. Remember this. Okay, so anyway, I hope. What does this show? What observation are you going to see? Right, essentially the observation, which you need to write, by the way, in your answer. Basically, you write something like this. Ki equals turns brown due to formation of I2. This has again come up many times. And of course, it may ask you to explain a bit further. Since Ki equals as for oxidizing agents, you can conclude that Cl2 is an oxidizing agent due to the color change. I think I said it a few times, but I'll repeat. Please remember these two guys, KMNO4 and Ki. High chance they're coming up, both of them, even for your practical. Okay, just one last substance of interest. Oh, questions, anyone? No? One last substance of interest that comes up many, many times as well, iron. Okay, for iron, it has three common oxidation states. Right, it can exist as pure iron 2 plus ions, or iron 3 plus ions. Now, of course, I can tag an OS to them. Michelle, OS for Fe. Good. This one, Michelle. It has a charge, it's an ion. Yes. Oh, but right, you should write it as +2 for OS. And of course, the last one is +3. What next? You should know they have a distinctive color. Singing color of Fe. Good. Danger, Fe2 plus. Yellow. No. Okay, it appears as green. Fe3 plus, Michelle, color. Must remember. It's either red, sometimes brown like grass, sometimes yellow. Now, so sometimes your question just tell you the observation, no? It tells you something like, okay, green to red. Okay, your solution changes from green to red. You like the traffic light. What's your explanation? Now, more likely than not, once you see green and red, you should think about your good friend iron. So basically, it implies iron 2 plus, which is green, has oxidized to iron 3 plus, which is red. That is the implication. That is what you should write in your explanation. Can. Remember iron? Any question? No? Okay, just give you one more reaction to look at. This is not common. Once in many years it may come up. Let's say I have this. Okay, balance it. Figure out who is oxidized and who is reduced. Or is it even a redox reaction? Okay, the question tells you to work out the OS, so you can't use other methods. Sarah, then? Now identify where's the oxidation and where's the reduction. Question done. There's a note. Aluminium is in the elemental state, so OS should be 0, just like iron. OS is 0. Come on. Okay, good. Okay, good. Okay, can we do? Okay, Sarah, I can go. Let me see before you go off. This one is not that. Okay, can Ninja, you're done as well. Xingling, you take a photo, send your answer over. I hope you're still there. Okay, bye. Oh, no need, no need. I just want to see your pairing up. Okay. Oh, yeah.